Wait, is this chapter what, 20?
This is chapter 19.
Oh, all
19.
right.
19. So we're going to use this circuit right here to go through impedance transformation and step up, step down. Just give it a little bit of a review on this. We'll just do that in impedance transformation. And sometimes I have to look over here. I got books. In fact, let me move my books over here so I don't have to look over. And if I need to, I can go to the document camera. Okay? So all you have to say is, hey, can you put it on a piece of paper? This is an open session. So if Jeff comes to me and says, hey, put it on paper, I'm lost. Just give me a second so I can switch over. I just have to change over a host to the other computer. And I will get that video splitter. So,
Charles,
yes.
if I could just ask at one point, some of us have open mics, and that's fine. But if people can switch to using muted mics and push and hold your space bar for like a push to talk button, it won't quite sound like I'm on the phone with some sort of creepy person who's breathing into the microphone all the time.
So what he's saying is you could put yourself on mute, and that should be on the bottom of your screen. So it should be let me stop the share. Let me see if I can go. Let me stop the share. Let me see if I can share this screen. Share screen. I'm going to see if I can share my screen here. That didn't work. Okay, let me just go back.
Click on Zoom.
Click on Zoom.
Share your screen and click on Zoom.
I did it in screen. See, that's what I just did, and it does not come up. So that's weird. Because I did. Let me try one more time. Share screen, Zoom. There's Zoom. I got the whiteboard.
Well, let me do it this way. John, on the bottom left of your screen, click on the mute button.
Do I sound like a creepy old man?
Now you're just breathing into my ear.
And then, John, I want you to do a test. If you put it on mute on the, let me just do this. On the bottom, it says mute down here, not your computer mute. There's a mute on Zoom. Does everybody see on the bottom left-hand side of the Zoom screen, there's a mute?
I'm aware I could do that. I just don't really want to do that.
Okay, that's fine.
I mean, if it's a major problem,
that's fine, John. That's fine. Everything's
I'll
good.
do it. You know,
it's all good. It's all good. All right, let me get rid of my
or just move your mic a little bit. That would help.
How's that?
I don't know. We'll find out.
All right, let's go back to here. Share. Okay, so basically I have a circuit here. It's a 4-to-1 ratio on the transformer. And by the way, thank you very much for that correction on the 110, John. I did. That was computer error, not me. It was not me. That was computer error. So
Wait, we're writing this down, right?
What's that?
We're writing this down, right?
Yes, I would recommend you write some stuff down if you need to, or you're going to participate in a second here. So you're going to be needing your calculators. You're going to need everything. This is not just me speaking. You're going to participate here. So, first of all, and since I have Mr. Martinez already activated on that, so Mr. Martinez, this 4-to-1 ratio, what is that, and what does that say about the transformer? Is it step up or step down?
I'm guessing it's a step up.
Okay. John, what do you think?
It is a step down.
It is a step down. Whenever time your number is larger on the left side than the right side. The left side, remember your left side, left. Well, that's your right. My left, that's my left. But left side of it, it is always going to be a step down. So that is a turns ratio. On a transformer, you have wires. Normally, your primary is always going to be black. Okay? This is for anybody who's going to be messing with transformers that have leads coming out of them. Your primary is always black. Your secondary transformers could be any other color that they want. Red, blue, yellow, green, purple. Depending on what you have. In this case, if you look at this transformer, if you look at this transformer, you'll see that it does have a center tap to it. That's this guy right here. So if I blow this up a little bit, and I say to you, well, let's first figure out, let's go back. Whoops, let me go back. Let's go back to figuring out the voltage on the secondary. Let's go figure out the voltage on the secondary on this side right here. Don't pay attention to this current. It's not on. I did not run the simulator yet. So this is a 4-to-1 ratio. I'm just going to move everything over. We have 100 volts on the, this is the primary. This is the primary side. Oops, hold on. I got somebody that just came in. I just admitted him. So that's the voltage on the primary. So I'm just racing things right now. I might get off there. Thank you. All right. So if we take, I'm going to get rid of some of this. So this is what we're going to be finding on here. By the way, it states calculate the following transfer values: CP, PP. PP is power in the primary. That's your impedance in the primary. ZP is impedance in the primary. Power in the primary. Current in the secondary, and power in the secondary. So we're going to find all this information. We're also going to find ZS. That is your impedance in the secondary, and we're going to look for the impedance in the primary. That's impedance. Anytime you have a Z, it is impedance, because we're dealing with AC singles. Impedance is it's the circuit reacting in a particular way due to an AC single.
Okay.
Okay, so the first thing is, and since John chimed in already on that, we're going to use the equation, if you remember back.
I don't remember, no.
Remember to have your notes if you need to. I'll put these down just so we know. NP over NS is equal to VP over VS. Now, there's an easier way to do this, and this is cross multiplication, whatever it is. Since we have a 4-to-1 ratio right here, we have a 4-to-1 ratio right here. The easiest way to do this is to take the 100 volts, and that's an RMS value. If it's not specified, it is going to be an RMS value. If it's going to be a peak, it has to say a peak value. Is everybody clear on that?
All right, yeah.
Divided to 4, what do we get? So 100 divided into 4, John, what do you get?
25.
25. 25 volts, what?
RMS?
RMS, yes. I'm getting better at this, aren't I?
Yeah.
All right, so we got 25. Go ahead, John. Jeff, go ahead.
No, you're doing great.
All right. So VRMS. All right. I'm just going to put an RMS. I kind of can't do an RMS. This is just a pain. All right. So we have an RMS value right there. Let's do a V peak. Mr. Martinez, how do we get V peak secondary? And that's peak. I know I spelled it wrong, but I'm going to put a big S over here for secondary. So what do we have to multiply to get it to peak? So we take 25 times what?
Times that?
Times what?
I'm not too sure.
Okay, it's fine. All right. Who's on here? Who do we have on here? I need to see more.
Brett's on.
Brett, are you there?
Yeah, I'm here. I'm looking for all my notes on this. I can't
Okay,
find
keep going. Let's get your notes.
Yeah, I couldn't find the impedance either.
We didn't do that yet. That's tonight. That's right now. We're going back a few weeks here. Remember, 2 weeks off is enough to make everybody just go like stir crazy. So
yeah,
we're going the old-fashioned way. We're going back and then we're gonna come forward. Okay. I just want to see who we have here so I can sort of list up John, Andy. I hit John. John, I already hit you a few times. Who else do we have on here? Jeff. Let's get, I know Jeff. Jeff knows the answer. What do we have multiplied by to get this to be a V peak on secondary? So it's 25. What do we have to multiply this to get to peak?
So that's a times 1.414.
That's right, 1.414. So if we take 25 times 1.414, 35.5.
Hey, Charles.
Yes.
What chapter is this again so I can find it in the book? I can't find my notes on
Chapter
this.
19. Chapter 19.
Okay. All right.
Excellent questions. Keep going with those questions. Okay, so we got 35. I'm going to get rid of, I'm going to put this down. I'm going to just get rid of this guy. Let me see if I can make this smaller. There we go. That works. And I think I can move some of this guys over. There we go.
Where did you get the equation? I can't find it anywhere.
Which equation? The one I just used?
Yeah.
All right. So when we talked about an AC single back in, I do believe it was, what was it, 13, 14, 15? I think it was 15, on chapter 15. We came up with, there was a bunch of different equations for define V peak, VRMS, and all that. Okay. So the one equation we had is, so if you actually want to find V peak, if you have V peak, that's equal to your VRMS times it by 1.414. Okay? Okay, Mr. Martinez?
Yeah.
Okay, now if you're going V peak to peak, that's going to be 2 times V peak. Okay? Makes sense?
Wait, V peak to peak equals what?
2 times the peak value. So peak to peak is 2 times your V peak.
Oh, okay.
Okay? So that's just some information for you on that, okay? I'm going to get rid of this so I can draw some more stuff up here. If we want to go from V peak to RMS, and we want to get a VRMS. And we want to get to V peak, what do we have to do?
V peak to V RMS
Yeah, we take a
multiplied by 0.707 or something like that.
Yep. Got it. Because if we take 0.707 and we multiply it, take that and move that to the other side, it actually becomes 1.414. You take the inverse of 0.707, actually becomes 1.414 if you take the inverse of that. So, does that make sense?
Yeah.
Okay. So that just gives you a little refresher on that stuff.
Thank you.
You're welcome. Ask these questions. That's what this class is about. You know, we'll get through everything. Even if I have to, you know, spend a little extra time with you guys, I don't care. We're going to get through this. We will get through this. All right, so we got 25 volts RMS. We got 35.5 volts peak, right? I'm just going to write that down. Give me a new color. Give me a green. So there. So we got 35.35, and that's the bad thing about that. I could probably type this in too. Let me see if I can type it in. There's a text box right there. So we got 35.35 volts peak. There we go, much better. All right. So that gives us our peak. So if we want to go peak to peak on here, all we do is come over here, and I'm going to do is put 35.35 times it by 2. Whoops, that didn't work. Times it by 2 is equal to 70.70. And that's how you do it. Okay, so far? Making sense?
Yep.
All right. More participation coming in. Okay. When they see ZS, let me just get this on the mouse here. You see the ZS. This ZS is also
Wait, where did we get the 2? My bad.
What's that?
The 35.35 times 2. Where did we get the 2?
Okay, so the 2 is we're going to go peak to peak. So that's where I got the 2.
Oh yeah. That's when you said multiply by 2.
That's correct, yes.
Never mind.
Nope,
Thank you.
nope, just keep going. Just keep going on that. It's an excellent question. Hopefully we didn't lose anybody here. Okay, so we have, you see the ZS right here. The ZS is going to be equal to your RL. So if you ever see RL, your RL is equal to ZS. ZS is your impedance on the secondary. Is there any questions on that?
So impedance is the same as resistance when there's only resistance in the circuit?
That's correct, yes.
So can you explain to me what RL is?
RL is our load.
Oh, okay.
That's your load. A load's anything you put something to. So let's say you hook up your smartphone to this circuit. That's a load. Okay.
Okay.
And the impedance would be a different formula, though, if we added in an inductor or something else other than a resistor.
Absolutely. You would have to figure that out. And that's where we're going to get into the next couple chapters in here. We'll get into reactance with the resistor, inductive reactance with the resistor.
Okay, thanks.
That'll be on 20. We probably should get that today. We'll probably end up getting that today because chapter 20 is really easy. It's going to be like, you're going to be like, oh, that's it. You know, it's really not that hard. So, all right. So RL is equal to ZS. ZS is our impedance. When we look at this impedance, this value right over here, this guy right over here, is actually reflected back to the primary side. Is actually reflected back on it. And what the primary side is some sort of impedance that is that we're going to calculate. We'll calculate that in a second here. So in your books, page 592, they give you an equation for your impedance. That ZP is equal to NP over NS squared. So I'm going to write that down. Let me see if I can write that down for you guys. Let me see if I can move this up first. I need more room. Oops. All right, let me just get this cleaned up here. Boom. Get that cleaned up. Okay. And I'm going to move this guy back down. Come on. It doesn't want to move. All right, never mind. I'll get that cleaned up, but you understand that RL is equal to ZS, right? All right. Let's do this. So ZP, that's your impedance on your primary side. To get your impedance on the primary side is you take your NP over NS. And I'm going to get myself one of those touch pads so I can just write this stuff out. Square it, times it by ZS. Okay. As a class, I want you to go ahead and calculate this for me. So NP, take NP and take NP over NS and square it and times it by ZS. See, and everybody tell me what you get on that.
160.
I want everybody to respond. Either you type it in to the chat, or you where's my chat? I lost my chat again on here. There it is. Or you respond just by just announcing it. Give everybody a second. I'm going to clean up this board here a little bit too. Let's see. Because I need some room. Andy, you there?
Yeah, I'm here.
Okay. What'd you get for that, sir? Did you get 160?
Yeah, just not.
Yeah, I got 162.
Okay.
160, I got 160.
Yeah. Watch those parentheses. Please watch those parentheses. That's the reason I'm asking if you're all having it, because a lot of times you're forgetting to do is put things in parentheses. There's a big difference if you just say NP over NS and you multiply it by ZS and you square everything. Or if you just, I don't know, there's many ways you can screw this equation up. So that 160 is ohms. So we have ohms on it, right? It is a value of ohms. So what this says is that the primary side sees 160 ohms reflected from the secondary. So basically the secondary says, I see 10, I'm reflecting back. This input right here says, oh, I'm actually 160 ohms. And we can prove that to you. Let's calculate ZP on this side using current. So if we take IP, so if we take C, actually let me redo that, hold on. Wrong equation. Let me try that again. So if I take ZP and I use current, ZP, sorry about that, is equal to, and that's ohms, I'm just using Ohm's law, V over R, V, C is I times R. Yes, IR relationship. Okay, messed up here. I need Ohm's law. Yeah, voltage over current. So first of all, we're going to find the current. So let's turn this guy on because we need the current. I would have to give it to you, by the way, if I wanted to. So if I turn this on, and I take that guy, where is that guy? There she is. I knew she was around here someplace. There it is. Can everybody see the 678 milliamps? Right here?
Yes, we can.
Right there. So that's 678. So we have 100 volts. So I want everybody to tell me what you get for, whoops, 678. And please do not tell me that's amps, because that would be a problem.
So what did you use to find the 678?
Sure. So this is a amp meter. I just made this an amp meter right here. So that's my amp meter right there. So let me get rid of some stuff on here. Let me clean up the board here. Okay. Moving things over. There you go. So this is right here. This XM1 is this meter. So I did stick this meter right into the circuit.
Oh, so you just divided 100 into ZP.
That's correct. Actually,
Okay.
not ZP, I. 100 divided into I. I'm looking for ZP, right? I'm looking for ZP.
I mean, because you have to find I first.
Yes, I just tossed in a meter in here and I turned it on to see what happens, right? Because this is a transformer. I don't need load over here. It's not going to short out because it's creating a magnetic field, right? So it shouldn't short
Yeah, but
out.
isn't ZP ohms though?
ZP is going to be ohms. So if we take voltage over current, that is ohms, right?
And we found that earlier, right?
Well, we did. I'm just verifying what we found on the using that equation on the top here. me get this out of the way. This
Wait,
equation,
so what-
right? I mean,
So what's
this
I?
I is current. So this equation right here, V over I, that's your current, and it's your voltage in your primary over your current in your primary. So if we do that, what do we get for a value?
$25.
Nope. We're looking for ohms. So this is going to be voltage 100 volts RMS divided 678.
147.
Okay.
Yeah, 0.147.
0.147. You're off because you forgot the mils. You forgot your mils. All right.
All right.
Got it?
Yes.
Okay. Now, if we came up with 160 over here, and this is actually 147, this is off by approximately a couple. Usually it work out a little closer, but we're using a circuit that could be. Let's see if they put anything. I'm going to see if they put any failures in this one. I don't think they did. No, no failures. Okay. Just make sure they didn't put any failures. No. Okay. So basically, we came up with 147. We calculated 160 ohms. So in reality, it is seeing about between 147 and 160 ohms on the primary side. So if you actually get this, and you do the ZP using the current, just tell me, I use the current value. If you use that big equation on top, which is assuming this one right here, I'm just going to move this. Come on, move down. There you go. ZP MP over NS squared times ZS. That's going to give you an approximation of what you're seeing over here. This gives you a more accurate reading of it. So we actually see between 147 and 160 ohms of impedance, and that's what the secondary is reflecting back. That's what the primary is seeing on that side. Any questions regarding to impedance? We're not
Still
done with
kind
this.
of processing it, so.
Still processing it?
Yeah,
You want me
that's
to repeat?
fine.
Do you want me to repeat it?
Oh, no, it's okay. I'm processing it.
A lot to take in, right? Mostly we've been off for a few weeks. That's why we're taking our time. Jeff, do you have any questions on that?
Yeah, Charles, the difference between the what was actually measured versus what was calculated, could that be explained by the transformer efficiency or eddy current? I mean, there was a bunch of stuff in the reading that suggested that we're going to have power loss through this whole process of the inductors and the transformers.
Actually, that's absolutely correct, because what you're doing is on using the measured values, you're using real world items, right? So if you're using real world readings, you got eddy currents, you've got losses on wire, there is so much that goes into the differences between the two, and that's always going to be the case. It's always going to be the case. The only way you're going to get something really accurate on these measurements, on these calculations, if you just use your measured values. But a lot of times what they have to do is they set up a circuit that's just like we did here, but they use a higher level math called calculus, and they get a little bit closer on that, to those values.
Okay,
yes.
but the measured value is never going to exceed the calculated value.
No, you should never. No.
Okay, thanks.
The measured value, the one that we measured over here, I mean, there's so many things that go into it. Eddy currents, heat loss, power loss, transformer efficiency, core efficiencies, how the transformer was designed with accuracy, there's so many variables that go into these errors. That's why when you get transformers, the more expensive they are, that means they've taken their time to make sure that all the windings are nice and aligned, like little soldiers. If you don't want that accuracy, you don't need that accuracy, then you're going to have a transformer that's going to be a lot cheaper. So, but if you want one that's really accurate, you're going to spend the money on it.
Okay, thanks.
You're welcome. All right, so we have all this. So 147. So if you came up between 147 and 160, we're only talking about 13 ohms of difference. That's not much, to be honest with you. It's really not much. So I'm content with what I have in these answers. If I came up with like 100 ohms here and 160 over here, that'd be like, oh, okay, what wrong with my measurement? Something didn't seem correct, but looks good to me. This looks good to me. So. All right, let me get rid of some stuff. We're not done yet because I could do this right here. I could do this. Okay, so I want to find the current I secondary. Oh, that's a big one. You didn't see that. There we go. So I want to do current I secondary. That's current. So I is current. So what's the equation for finding current in Ohm's law? Anybody? Brett?
I'm not sure. Sorry.
Okay. John?
Sorry about that. I'm back.
What's that?
Had to run to the little boy's room.
That's fine. We'll take a break here in a minute. How do we find current? If you're in DC, if the DC class, what's the equation for current?
Volts over ohm.
Yes. So voltage in the secondary over the ohms. In this case, we're going to call it. I'm just going to use the word ZS. You could use ZS or RL. And this doesn't matter if you use ZS or RL because they're the same, right? They're the same here. I'm getting there. So we have what? 25 volts RMS. I'm going to use all RMS values here. 25 volts RMS. And you tell me what you get on this. Over, what is it, 10 ohms? I think it was 10.
Yeah, it was 10. Wow, that's a lot more current.
How much current did you get?
2.5 amps.
Yeah, it's a lot, 2.5. But look at what your ohms are. It's like only 10 ohms. So yeah, that's like running a light bulb, right? That's I don't know if that. Well, that's a little high for a light bulb, but still 2.5 amps. That's a circuit you don't want to be messing with. Really, you don't want to be messing with that. So, okay. Any questions on that so far? Let's see what the measure. Let's see what we get when we run this thing. This thing is running right now. I'm gonna clean things up here. Get rid of that, and I'm gonna put it in a new meter because that's a volt. That's telling me there's 24. Actually, I can keep that. I'll just go with that. This is saying that there's 20. Yep, there is 25 volts, which is we calculated. And this says it's about 2.5 amps. So our measurements would help if I put my units. This measurement is meeting that guy. This measurement is the same as that guy. Pretty neat, huh?
Yeah.
Okay, impedance matching. Let's see what we have left in this chapter. I want to go through. Just a little bit left in here. That's not much. Okay. All right. So real quick on impedance matching. Impedance and impedance transformation. Impedance matching. Let me think of how I want to push for this impedance matching. So impedance matching is basically using similar equations. The only difference is that what we're doing is, let's say you have a an amplifier, and we're going to connect it up to some sort of antenna. We need to make sure that the load resistance, the impedance resistance of the amplifier and of your antenna are matched together. If they're not, then you're going to have unmatched, and you're going to be drawing a lot more power, which is not good for your amplifier. And that's what impedance matching does. So we want to do is we want to match it, so we try to get it equal, so we're not causing the system itself to overload. So that's what impedance matching is. I'm just seeing how much I want to cover on that. Okay. Who needs a break? Can we go another 10 minutes and take a break?
Yeah, that's fine.
Okay. I'm going to do is I'm going to try to switch screens. Actually, let me try this. I'm going to stop the share. Any questions in regards to this circuit at all? That covered. Then it covered impedance transformation. And it covered the transfer ratio, calculating all of the peak to peak, RMS, impedance transformation, current. Anybody have any questions in regards to that?
I think it's pretty fine. Just got to do more.
Just got to do more? Okay. And I'm going to extend the homework out on chapter 19, and we're going to get to 20. And probably won't get to 21 today, but we'll get to 20 today a little bit. Okay, let's do this. Let's see if I could do a... I'm going to see if I could do this. Okay, I'm going to stop the share on this one. And I'm going to go share whiteboard. Boom. Let's see. Boom. Okay, here we go. All right. So I am going to draw a box. Let's just get a box. Is that a box? I think it's a box. Okay. There's a box. Okay, that's our generator. Let's call that our generator. And our generator, let's say, has it has an RI. It has a small RI. That small RI stands for, that's the resistance of the generator, okay? And that has to be a value you have to be given. If you can calculate it if you had the right tools to calculate it, but that comes with those engineers that design the system. So the RI is something that engineers will look for when they're designing it. So we're going to say RI is equal to 200 ohms. Okay. So let's say that our load is out here. Our load is going to be equal to, let's say, 8 ohms. And let's say that this, let's say the generator is running voltage at the generator. That's VG is voltage at the generator, and let's say it's 110 volts. Let's say it's 110 volts on it. Okay. So basically, this is the resistance of the generator itself. That's 200 ohms. Extra credit for people. Hold on. All right, so there's our equation. So what we're going to calculate on here is our power of our load. So we want to do power of load. I'm just going to push this. Whoops, power of load. And this is power of load. And that's going to be equal to, and I got to draw this out. So the power of the load is going to be equal to the voltage at the generator divided into your resistance of your generator plus your R load, and that's this guy. And then you square it, and then you multiply it by your RL over here. And that's your power of your load right there. So if we take,
Charles, what
yes,
page
Yes.
is this on?
this is on page 595.
Thanks.
You're welcome. So what this power of load is, we're looking at is the power of the load. This is this part right here. So this is the PL we're looking at right here. This is not the power of the generator. This is the power of the load. So we're taking the voltage generator times divided by the RI plus RL, and then we're squaring it and multiplying by the RL. So what we're doing is we're looking at for the power of the load on the side. So using the information I gave you up here, go ahead and calculate the power of the load for me, please. Andy, what'd you get for the answer for that? How about you, Brett? Can you tell me what you got an answer for that?
I'm still putting it into my calculator.
Okay, that's cool. Give you more time.
I got 2.237.
That's what I got. What's the units?
I got 584.
584? You're a little high. Just a little bit. Try again. Remember,
Watts, yeah.
I'm just waiting on to make sure everybody had the answer.
Yeah, I got the same.
Okay. Okay. Let's do this. All right. So now we want to do is look at our NP, and we're going to say NP over NS. And I'll explain to this one in a second to you guys. Oh, you can't see that. Should have moved everything up. Okay, let me do it on this side here. Okay, if we take NP over NS is equal to the radical. I'm going to explain this equation. This one actually refers back to the impedance transformation, ZP over ZS. So let me explain what goes on here on this. So first of all, ZP and ZS are in ohms, because that's our impedance. Everybody agree with me on that?
Yes.
Okay. So if we're saying that if we could take the impedance of the primary and the impedance of the secondary and square it, that should be equal to the NP or NS over here. So let's see what happens over here. So if we take and we have 200 ohms in our primary over 8 ohms in the secondary. Yeah, razor. And we take the radical of that. What is the ratio do we get on that? So first of all, if we could take
5 to 1.
it is a 5 to 1. It is going to be a 5 to 1 ratio.
It's a 25 to 1, isn't it?
25. Well, okay, it's you get 25, but you forgot to take the radical of it. So if we take a 25, now we
yeah.
so now we get is 5 to 1 ratio.
Yeah, you're right.
Okay. All right. All right, so the last part of here is we're going to send up, we need to get, so this is, let me just get these values down for you for here. So we can say that this is ZP, and I'm going to say this is ZS, because this is where we just finished up finding. Does everybody agree with me on that? Which is equal to NP and NS. Let me actually write that, yeah, let's keep it that way. So that's just figure everything out. Good to go? Okay, last part, and then we're taking a break because everybody, We need little stretchy legs. The last part of here is going to be the power in the primary. And I'm going to get better at this. I promise you I'll get better at this. So, I'm going to go over here on this. I'm going to move things around. I got too much going on here. Okay, so if I want to do is figure out this is the power and the load. And now what I want to do is figure out the power in the primary. Come on, get over there. Okay, let's do it this way. Power in the primary. Power in the primary is equal to, and if we take the voltage in the generator over the resistance of the generator plus ZP, and we square it, and then we multiply it by ZP. You notice that if you look at everything, here's the primary, we're doing everything in the primary. Everything is related to the primary. So in this case, we are going to get the voltage in the generator. Okay, so I'm going to put so what's the voltage generator we have?
110.
110. And everything's going to be, and then we have that divided by, what's Ri? 200. And our ZP, what's our ZP?
5.
5. So you notice that these are all in ohms. I'm going to clean this up here in a second. Let me clean this guy up. Remember, this ZP is still 5. So we can say that is 5 ohms. So we got ohms plus ohms. And then we square it. And then we multiply that by ZP. And ZP is going to be multiplied by 5. So if we do all this math, what you guys get, and then once we get that, we're taking a break, and we're done with. I'll talk, but we're not done yet. But we'll get close to done with 19, and then we'll jump to 20 just real quick. 20 is going to take
2.78.
What was that?
2.78.
2.78. Okay, and that's watts. Okay. Let's make sure everybody had that, and I'm going to make sure that too.
I got 1.4.
Okay. That's why we're doing this together. Hold on, I didn't hear that.
1.439.
1.439.
Yeah.
Okay. $1.439. Mr. Martinez, did you get that? Daniel, did you get that?
What? 1.439? No,
Yes.
I got 2.78.
Yeah, I know you got. Can you recalculate it to see what you did?
Yes, I can.
And then we're going to take a break here. And then we'll finish up the 19. And before we take a break, I'll explain to what you just calculated on here.
Yeah, I got 1.43 now.
Excellent. All right, so basically what we're doing is what we did here, and this I did not show you yet, is what we did was in order to match the generator with this load, what we did is this equation right here this is your transformer equation. So we use a transformer to do the impedance matching for us. That's what impedance matching is. You're using some sort of inductive load, such as a transformer, to match the primary side to the secondary side. In this case, as you can see, is this case did I do that right, ZP? Yeah. Hold on. Did I do this right? Yeah. Yes, I did. I think I did it right. Okay, so if I did the ZP and I use this equation, this would we get correct on it. Now, if I actually put in a transformer in here, I'm going to try to do this. That's a transformer, by the way. And let's say we put on this side another transformer. And let's say we had a turns ratio over here. We could actually do some impedance matching much more efficiently on this. So that's what impedance matching does. So you're using an inductive load transformer to match your source load to your source to your load. Does that make sense?
So how did you get that your matching over here for this one?
Which one?
Your matching impedances over here on the top right?
This guy right here?
On the other side.
This one?
Yes.
Okay, so NP over NS, I took the ZP over the ZS. So that's what I was saying to you. I was just using the load I had. So in this case, I'm just taking, for example, just as an example, a ZP and ZS that I have. So this case, I'm using ZP is 200 ohms and this RL is 8 ohms. In reality, what you do is you have a transfer ratio 4:1 right here. So let's say we use a 4:1 ratio on that. Could we do it that way?
Oh, I see. Okay.
All right. So if we stuck a transformer in there with a load on it, and let's say this RI right here would be my ZP, okay, and my ZS would be 8 ohms. That's how I came up with this guy right here.
Okay, I see that now.
And I think I made a mistake on something on here.
Yeah, it's
Yep,
giving
I
us a
did.
5-to-1.
This is wrong right here, folks. Yeah, this is supposed to be 200. I made a mistake. That was supposed to be 200 because that ZP is right here. Remember that ZP is right here? That's my ZP right here. That's
But isn't that after you calculated though?
Well, I was using the wrong numbers. This is finding the turns ratio. This is my turns ratio. This case, this turns ratio is 5:1.
Oh, that's your NP and NS.
Yeah, that's my turns. That's my thing. I thought it was 5. Why did I put 4? That's supposed to be 5:1. That is, I don't know why I did that. That was dumb.
Oh.
That was dumb of me. I probably screwed you guys up. So this guy right here
So I'm guessing it would be
is that we did right there. With that we did. The ZP and the ZS has to be where you use these guys right here. That's where I made mistakes. This is supposed to be 200.
So the NP and NS is 5:1.
Yes.
And the ZP and ZS is 200 to 8.
Yeah, that's supposed to be 8. I made a mistake. I was using the turns ratio.
Oh,
My
okay.
mistake. My mistake. So let me clean that up, and I'll show you what it's supposed to look like.
So it'd be like RI plus RL parentheses square root by times EP.
Yeah. This is going to be 8 ohms. And this is going to be, what was it, 8? This will be 200.
So that's 55.994.
Thank you. My apologies. What'd you come up with? 55.94.
94.
Okay.
That means RI and ZP are both the same thing.
Yes.
Just another way of putting it.
Yes, that's correct. All right, let's take a little break. And then we'll finish up this chapter, and then we'll hit 20. And then 20, we'll do a lap. Sound good?
All right.
Sounds good. About 5 minutes.
5 minutes. I'm going to stay on video, but I'm going to mute for a second so you don't hear me chewing food.
Hi, Carol. This is Jeff Hens calling. I had a message you called a moment ago. Yeah, I already went and saw a cardiothoracic surgeon out at DuPage. Somebody else who was through my insurance network. When I didn't hear back from Dr. Telfer, I figured I'd just find somebody who was covered, and made an appointment and went out and saw that person, Dr. Tomasco. Yes, he is. Yeah, he took a look at it and said, they're going to basically rescan me in 6 months, which I guess is coming up in another month or two. Repeat the CT scan, and then if things aren't changing or they're changing very slowly, his recommendation at this point was just to continue monitoring. He gave me a couple of things to avoid doing, but he wasn't. He went through the whole thing and was saying that from his perspective, my ascending aortic artery looked totally enlarged as opposed to ballooning. Ballooning would have been an issue. Totally enlarged, it may just have always been that way, and I've never had a scan before to show it. So he said, yeah, we'll just watch it, and if it looks like it's starting to balloon, or if it looks like it keeps getting larger, then that's an issue. So, yeah. Yeah, I'm supposed to go back and see my pulmonologist at the end of this month, at the end of April. That's where all of this started, was with the pulmonologist. And he was trying to figure out where the cough was coming from and all the rest. And he thought it might have been a GERD issue and put me on PPIs, but that doesn't seem to be doing anything. The cough is the same. All the PPIs are doing is making me constipated. So, yeah, he's going to go next. I did have a question, though, for Dr. Telfer, and I don't know if this is something you can pass along to him, but maybe ask him. When he first started caring for me, he had me on beta blockers, and then switched me over to other medications. I'm forgetting the names of them off the top of my head. To try and get my blood pressure down a little bit, because he thought the beta blockers might be contributing to the cough. And my question was, my blood pressure still isn't quite where it needs to be. Every time I go in to see the doctor, it's up in the 135 range rather than the 120 range. When I was on the beta blockers, it seemed much better. Is there any reason that I could try going back on the beta blockers to see if that would help with the blood pressure? Because quite honestly, I'd rather live with a little bit of cough and have my blood pressure where it's supposed to be than the other way around. If that question makes sense. Yeah, if somebody could give me a call back on that. It wasn't worth making an appointment over, and these days, who wants to go near the hospital anyway, but I figured, sure, and we could set up a telemed appointment if he thinks, but I just, the one piece that the cardiothoracic surgeon, Dr. Tomasco, said was, among other stuff, keep your blood pressure down. And I said, okay, well, when I was doing the beta blockers, I was in the 110 to 120 range constantly, and now I'm in the 120 to 135 range. Well, again, Dr. Telfer thought that because I had been diagnosed with asthma, he thought that the beta blockers were contraindicated. However, the CT scan showed, among other things, my lungs being perfectly clear. So the asthma, again, I'm just guessing here, but when I was a kid, I had allergies, dust, molds, and pollens, and I had years of allergy shots, which supposedly took care of all that, but I don't think it really did. I think what's happened over time is that my allergies have mutated from runny nose and puffy eyes into coughing and wheezing. Yeah. And that, unless it gets really bad, I don't get runny nose and puffy eyes anymore. I just cough a lot. So I think this is still an allergy thing. More so because when I get like that, if I take Benadryl, I feel better. I mean, I feel dopey from the Benadryl, but I feel better, symptom-wise. So they're calling it asthma, but I don't think it's asthma like, and he's got me on steroids anyway for the asthma. But I'm trying to find a way that I can get my blood pressure down more effectively, and whatever he's got me on now, I don't think is quite getting there. Okay. I'd appreciate it. Thank you very much, and I appreciate the other call. Thanks. You too. Bye-bye.
Did we lose anybody in here? Who did we lose? Daniel, John. I think we got. Who do we miss today? Who was not in my class today? Michael's absent. Dominic's absent. Brett's present. Ori is absent. Daniel's present. Nathan. And he is present. Everybody else is good. All right, let's get the screen. Gotta get a screen. How's everybody doing? We back?
Yeah.
Back.
We're back. Okay. Make some ramen. Hey Brett, when you're making some ramen noodles, send some this way. Could use some food. All right. We're gonna begin back here. How am I doing? How am I doing so far? Give me a thumbs up. Give me a thumbs down.
You're doing good.
Doing good. Okay. Andy? I think he's still there. Hopefully he is. Hold on, I gotta do a. What's everybody? Hope you don't mind. Whoa! Why did that thing do that way? Hold on. Don't ask. It's for the college. There we go. All right. Still learning all the toys. Okay. They want photos. Try to get some spirit going left. I don't know. All right. You ready to get going back here? Let's go back. Okay. Let's do this. Okay. All right. So we got inductors in series, inductors in parallel. If you are going to remember, a inductor is measured in henries, and the units, the symbol is L for inductor, and H for the units, which is henries. So hold on, I gotta do something here. Oh, great! I was recording while everybody had. That's okay. All right, let's do back to the share. Boom, boom, boom. Okay, let's get this done. So if you have inductors in Henry, inductors in series, you add them together. So basically, you just add them together. And annotate. So text. So this would be L1 plus L2 plus L3. Oh, L3. Good to go? Okay. Inductors in parallel. Inductors in parallel, and I have to do it this way. This would be that equation 1 over. I'll just keep it red. And then parentheses 1 over L1 plus. Do you think you'd do it a different way?
Yeah.
Yeah. You could do it also. That's nice. What's wrong with my bottom equation?
It's not in parentheses.
There you go.
Well, and it'll only work for 2 inductors.
Yes, it does work for 2 inductors, but can you use it for 3 inductors?
Yeah.
You can. You can. Let me show you how to do that. So basically what you do is you take L1, let's say you have this guy right here, take L1 times L2, and then you take L1 over L2. Well, that gives you this one. Now what you do is you take this equation, let's call this L1. Yeah, I'm going to move everything over. That didn't work. That's not what I wanted. No, it went upside down. I don't know what happened here. All right, let me just rewrite it the other way. But you saw the first. That was alien, by the way. That was just weird. All right. What you do is you take L1 L1 times L2, L1, L2 over L1 plus L2, and you call this equal to, let's call this L1 comma 2. Now you have this one right here. Just ignore L4, 5, and 6. Just pretend those are 1, 2, and 3. Now what we could do is take L1 comma 2 multiply that by, because I'm just keeping this parenthesis here so it's not confusing, L3 over L1 comma 2 plus L3. That works that way too. Different ways, everything gets there. It gets there, right? Mathematics is fun. Mathematics is fun. Any questions in regards to transformers?
I don't think so.
Okay. Eddy currents. Eddy currents are straight currents resulting from space of heat. Eddy currents are waste. Eddy currents is a result of the back EMF that's coming off the transformer. And it's waste. And the only way to get rid of that is to, number one, is to do impedance matching. If you don't have proper impedance matching, you get a lot of eddy currents. Very bad, very bad. The other way to do it is to cool your transformer down. The humming of the transformer is due to the laminations in the transformer actually vibrating. It's pretty cool. So, let's see. Measuring. The rest you will just go ahead and do. If you didn't get chapter 19 homework done, go ahead and finish that up for, let's say, next week. I'll put D2L up and we'll get it cleaned up for you on that. Sound good?
Yeah, thank you.
All right. So no rushing on things. No rushing on things. Okay. We're gonna get into We're going to head into chapter 20, inductive reactance, in a second here. We did a lab already with the transformers. We did a lab on 19 with the neon lamps. We were lighting those things up because of the high voltages. And I think, Jeff, we were using your station to see how much voltage we actually were producing. I think it was 300 volts. Yeah, that's not a game. I mean, that's some serious stuff if you actually look at it. I mean, these transformers that we have, this is about 1 Henry. So if you look at the primary side, that's 1 Henry. And if we take this and let's say we use the secondary side, that could be, another half a Henry, or 500 mils. So get these, you start putting these in series with each other, boy, you can have some serious high voltage at the end. Because what's creating on these transformers is you are building a magnetic field. That magnetic field has to go someplace when it's done. So, I mean, it doesn't see this as a step-up transformer initially. It just sees this as just a coil we're making some magnetic field. It sees 1 Henry. But once we shut it down, it says, oh, now we got like almost literally a step-up transformer going on here on this side. So it kicks it off. Make sense? Okay.
Yeah.
All right. Clean my board up here, eraser. All right. So with that said, so we got inductors. Let's do an example of an inductor in series before we actually move on. So what would be the answer to this one? Somebody give me the answer to this one right here. And somebody give me the answer to this one right here. So Brett, give me the answer to series, and I don't know. Andy, you there? Okay, can you give me, do you want to do the parallel for me?
Charles, did you say you want me to do series?
Yes.
Okay, 1 second. I'll get my calculator.
Okay. Jeff and Andy, you can do the parallel one for me.
Okay, so for the parallel one, it's 0.3. And I did that just by, since they're all the same value, took that value and divided by how many inductors I had. So 1 divided by 3.
Good. 1 and 3. Good, because they're all the same, right? Yeah, they're all the same.
So, Charles, I wasn't here for the explanation of how to do this series. Is it literally just L1 plus L2 plus L3?
Yep, that's it,
Okay.
sir. Yep.
Then 3 millihenries?
Yep. 3.
Okay.
Good. Any questions in regards to those henries? I do got some ductors, but the problem is I don't got a machine here, and I haven't taken the machine yet from the college. And yes, I am going to borrow that machine from the college. We're going to have some fun. So, little ductor. I got ductors. We're going to be using those. All right. Let's keeping this into chapter 20 is inductive reactance. Inductive reactance, and by definition, inductive reactance. Well, let's first understand what we're dealing with. An inductor, when it sees an AC single, is gonna have a counter EMF to it, right? It's gonna say, oh, it's gonna react to this AC single, like a capacitor. So basically, the inductor reactance is the result of inductor's counter EMF with varying current. That's what the definition of the book is. So it is a counter EMF. So when we look at inductor reactance, I'm going to stop the share on this. I'm going to see if I can switch shares. I'm looking to see if it'll let me stop. I'm going to stop share. I'm going to go over to another share. Whiteboard. Share. Whoa. There we go. Cleaned up the board. All right. So first of all, when we deal with inductive reactance, we're dealing with an exabel. An exabel is called the inductive reactance and is measured in ohms. Okay, so this exabel, like a capacitor, when it sees an AC single, it acts way differently. It acts different. So when it sees this, it's gonna, we know that when we put an AC single to the to an inductor, there's gonna be a. Let me put it this way. I'll throw it on here. There's an AC single. So basically, you're going to have a magnetic field that's going to be created one direction, and they're going to have a counter EMF going in the second direction on it. Because of that counter EMF, because of this thing varying so much, this inductor is actually going to see this is going to act as it's going to see this as an ohm. So, for example, exabel, equation for exabel is equal to 2 pi. And 2 pi is due to the fact of we're going from here to here. Ooh, that's bad. So remember that's this is 2 pi because there's 0, there's pi, and there's 2 pi. So that's 2 pi times by our frequency. Well, because we're an AC single, we have a frequency. And we also have an inductor, 2 pi f and the L. 2 pi FL. So that's where the 2 pi comes into the fact. So just like in a capacitor, this inductor is going to act like some sort of resistor. It's going to have some sort of resistance. We call that inductive reactance, and then measured as in ohms.
And the L is length, right?
Nope. L is your inductor.
Okay.
And then we're going to use millihenries. I'm going to do an example here in a second, okay? So I'm going to clear the board here for a second. And
What's F?
what's that?
What does F mean?
F is frequency. Good questions. Frequency. Whoops, you can't see that, can you? There you go. I got a second screen here. I'm constantly looking over to see what you can see and I can see. So that's why I'm bouncing my head back and forth. All right. So let's clear the screen. Whoops, clear the screen. Drawings. All right, I'm going to go to the top here. I'm just going to move some stuff out of the way. All right, so if I say x sub L is equal to 2 times pi, there you go, times your frequency, times it by your inductor. So that's the equation we use, right? 2 pi FL. So if let's say that we have a frequency, a frequency of 1 kHz. And our inductor is equal to 100 millihenries. So we want to find x sub L. So you solve for x sub L. So what do we put in here? Somebody tell me.
Um, 2 pi times 1 kHz times 100 millihenries.
Okay. What'd you guys get?
$628.
628. Yep.
Yep.
And that's in ohms, right?
That's right.
So this inductor, what we're saying here on this is that, and you can put this in the chat too, if you want to, you can put it in the chat. I'm watching the chat now a little better. Basically, this inductor, when it sees 1 kHz, when it says 1 kHz single, it doesn't matter the voltage. This 100 millihenry inductor, when it sees a 1 kHz single on AC single, it reacts as a 628 ohms of resistance. Want to do another example?
I know, it's pretty self-explanatory.
Jeff, you talking? I can't hear you.
Okay, can you hear me now?
Yeah.
Okay, so sorry about that. So is that resistance constant over time, or does that resistance change over time?
As long as it has a 1 kHz single, and it does, as long as that 1 kHz single doesn't change, it's not going to. That'll stay the same. That'll stay the same.
Okay, thanks.
Now, in the real world, what happens to inductors as we're constantly putting some sort of load to them or some sort of voltage to them? What happens to them over time?
They heat up.
They do heat up. They do break down, right? So inductors, when they start breaking down, usually it's over time, it's going to be the Henrys itself. It's going to, instead of getting 300 or 100 millihenries, you're going to start seeing it decrease off of time a little bit. It takes a long time. Now, if they short out, then it's dead and you fry it, right? Then they're fried. To check an inductor to see if it's actually working, there's only two ways to do this. Use an ohm meter. You should get some sort of ohms to see if it's still there. Because a lot of times what happens, these inductors inside, the wire, the enamel inside will melt off and they'll short out to each other. And then you'll get some strange readings on your millihenries. That's a good sign that your inductor has failed. The second thing that can happen is the wires actually melt or open up and then you have it open. So you can have a short circuit inside. The short will actually cause the henries to change because you now no longer have the same amount of turns. And the second thing that happens is you can actually short it out, open it up, and then it's, and then you get nothing on it. So there's two things that possibly would happen. Number one is more likely than number two. Number one is more likely than number two. And when that usually does happen, you get a very high increase in current. Because remember, your ohms is changing. So your current's going to react to that, so you're going to bounce up on current. All right. Exabels in series and exabels in parallel. So exabels in exabel total, just say exabel total. And that's going to be, you'll take exabel 1 plus exabel 2 plus exabel 3. So first of all, let's find the exabels here. Let's say our frequency is going to be equal to, let's keep it at 1k hertz. So what is the exabel 1 right here? So John exabel 1, Brett exabel 2, and who else do we have on here? Mr. Martinez exabel 3, and Andy, you could do exabel 3 too with Andy. So you tell me what you get.
I don't get it, so I gotta use one.
Exabel 1, let's do the exabel 1 first. Let's do exabel 1. Exabel 1, the equation is 2 pi. We're just looking for the inductive reactance at 2 pi f.
Oh, I get it now. My bad.
Okay. All right. So go ahead and do exabel 1. Everybody give me some numbers on that. Okay, what do we have for XBL 1?
628 ohms.
XBL 2? Andy, your decimal is off by 1. Good try on that. Jeff, is that the second one?
188.
Yeah. Is that this one? So Andy, it looks like what you did is you possibly forgot a 0 on your mils. Who's doing XBL 3?
It's 6.
Me, I got 6 point.
What was that? What'd you get, Daniel?
6.28 ohms.
Got it. Okay, 6.28. Excellent. Okay, 6.28. Good. Excellent. All right. So we got 628, 188, and 6.28. So let me go back to my mouse. Get these guys. I did it again, didn't I? I'll fix it. I'm moving things up. Okay. That's XBL total. Just gonna erase that. Okay. All right. So what do we get when we add all 3 of these guys up together?
$822.
Okay. $822.
0.28.
0.28. Was that you, Mr. Martinez?
No, that was John. I got
John.
80,
Okay. Okay. So,
822.28.
okay. Brett, what'd you get? Somebody has a nice dog in the back row.
Sorry about that.
No, it's no problem. Brett, what'd you get for this? All right, I'm just gonna. The miss stepped away, and then so that's correct. All right. Any questions in regards to that one? So I just went through with you. So I gave you some inductors. You found the inductive reactance, and then you found the total inductance of the circuit. So the circuit sees 822.28 ohms of resistance based on 1 kHz single. Pretty nice. Not bad. Okay. Remember our values because I have to clean my board up here because you'll see what I'm doing in a second. Okay. What do we get for this 1 Henry? I'm going to get rid of this over. Boom, delete. Okay. Okay, what do we get for 1 Henry again for XBL? What was the value?
6.28.
6.28. So on this one, to find the exabels, you do the exabel total for parallel is similar to this. You just do the 1 over exabel 1 plus exabel 2. So on this one, you could, since we only have 2 inductors, can you just do the multiplication together? Like, can you do it this way? Could we do it that way instead? Yes, no?
Sure. But we could also just divide by 2 since their values are the
There
same
you
and there's
go.
only
You
2
could
of
do
them.
that. Yeah, you could do that. There's a third way. So you get the third value. So you take the number of exabels you have, right? The exabel value. If these are the same, you just add, and divide by 2. If you had 3, divide by 3. 3 different ways of doing it, right? So 6.28 divided into 2 gives you 3.14 ohms. Hey, it's pi. There's pi. All right. Let's any questions?
When you mean XL over 2, is it like everything? Like the
Well, you see how these are 6.28 are the same here? You see how this 6.28 is the same right here? If they're the same value, you could just take the number you have over here, if they're the same value, and divide by 2. So if you had 4 of these as 6.28, you divide by 4, right?
Yes.
Okay. So, but if these were different, you can't use this equation right here. You would have to use either this one or this one down here. Okay? Good job, Andy. Okay. All right. Let's see if we can do here. Just give me 10 seconds. Yeah, you guys would hang me on that one. You would just be like, what did he just do? Let's see. Okay, there we go. Last thing we'll do right here, screen share. Boom, boom. All right, got some inductors. This is just, what we're gonna do is, let's see, we got 100 mils. Do I want to do this? Let me see what the other lab is. I sent you guys, did you guys get the email from me today about the labs and all that? Those lab sheets, the PDFs and all that?
I haven't checked it yet.
Okay.
Same here. Yeah, I haven't checked.
Okay.
Yet.
I'm looking for something to see if I can find it. I have it, it'll be great.
Yeah, it came through, Charles.
It did come through. Okay.
Yeah, I'm just looking at it now.
Yeah, I got it too.
Okay. Let's see what this one is. Okay. I'm going to do something here, put this up instead. Okay. So this was one that they wanted you to do. I don't think you guys did this in lab, did you, at all? Is that correct? Inductive reactances and all that?
No, I don't think so.
Okay. Inductive reactance XFL, inductive reactance, series inductive reactances. Okay, all right, let's do this. Let's calculate the exabels for this circuit down here. I'm going to see if I can go full screen on this. That didn't go the way I wanted. I was hoping to go full screen on it. Let me see if I can go full screen. I'm going back. Okay. Share again. Let's try this one last time. PDF. That's Adobe. Okay, that's Adobe there. Share it. Hopefully that's Adobe now. Get off. Boy, my computer doesn't like me today, folks. There we go. All right. Can you? What are you guys seeing on there? You're seeing. There you go. Weird that you're seeing that. Okay. All right, real quick, we'll finish it up. We'll finish this up. We'll do a little bit of this one. See if this is the one I want. Exabels. Yeah, we'll do the bottom part, inductive reactance. We'll do this series one, and next week we can pick up the parallel one. I'm gonna get over there. All right, so exabel 1, exabel 2, and exabel 3. So right here, you guys are gonna tell me what I'm gonna put in. So what I'm gonna do is this one right down here. We have 33 millihenry and 100 millihenry, and we have 5k hertz. So find me exabel 1, exabel 2, and let's see what we got.
Could you scroll down a little bit?
Oh yeah. That's not what well, that didn't work where I wanted to. Is that any better or is that worse? I don't like that. I don't
That's a
like
little
that.
much, yeah.
Yeah, it was too much. Okay. Let's see if I could. Is that better?
That
Yeah, you
works,
just-
Charles.
Okay.
Yeah.
There we go.
XL1, I got 1036.
Okay. 736.
No, 1036.
1036. Okay.
And L2 is 3141.
Is there an XL3?
No, that's XFL total up there. Okay. So what's XFL total?
$4,177.
4,000 what? 77 you said?
Yeah, 177.
Okay. All right. Let's since we have all these, we have XFL total is 4177 k ohms. Let's get the current I total. I total is equal to the voltage total, RMS, divided into X of L total. So go ahead and tell me what X for current is. What you guys get for I total?
1.2 milliamps.
1.2 mils. Everybody agree? Jeff, do you agree?
Yes.
What do you get I total? It's voltage total over what?
Voltage total over XFL total. So you take 5 volts all over 4177. Okay. VL1. That's just your current total. Times that by your X of L1. All right, so give me VL1 using this equation, and give me VL2. Who hasn't? Brett, can you give me VL1?
Yeah, I'm working on it.
Okay.
I'm not sure. Sorry.
Okay. So somebody John, can you give me, or Jeff, one of you two, can you give me the answer to VL1 and how did you solve that?
You just find the volts. So if you know the ohms and you know the voltages, you're just gonna multiply your.
Are you saying you're using ohms times volts, or are you saying ohms times current?
Ohms times current.
Okay, it's better. Okay, so what'd you get for that then?
1.2 volts.
Okay, 1.2 volts. Okay,
Yeah,
1.24. And Jeff, what'd you get for the second one?
So the second one is 3.76.
3.76 volts. Okay. Add these two up together, Mr. Martinez. Add up 1.24 and 3.76 and tell me what you get.
$4.96.
4.96. Does that come close to the 5 volt RMS? Does that come close to does that come close to our source voltage?
Yeah, that's pretty close.
That's pretty close. All right, let's do this. All right, let me pull off the share on here. Let's set the circuit up and let's measure. Let's do some measurements, see what we get. Hopefully I got the right inductors. I don't know, find out. I gotta switch over on somebody here. I gotta go to virtual me. Make host, yes. Okay. Okay, here's the circuit. What I'm going to do is I'm going to separate these out a little bit. I'm going to put in I'm going to put this as a series so you can see it a little better, and that way you get see it. So basically, there's that. There's my generator. I'm going to go ahead and put my generator. All right, there we go. A little bit of a delay, isn't it? Okay, so this is my 100 millihenry, and this is my 33. And let's see if I can get this guy. This is really tricky, you know that? Boy, I'm getting some serious delays, aren't I, on this? I'm going to back it out just a little bit. Okay. So I have a DC. So my my function generator is over there, and you can't really see that. There you go. A little hard to see, but it is set up for 1K hertz 7.07 because remember my function generator is a peak, right? It's a peak value. So I'm going to do is move this over. Okay. All right. That's AC. And I'm going to measure the voltage on this guy. And what do we have for our value for the first one? What was it again?
1.24.
1.24, so we're coming up 1.13. That means this inductor's off a little bit. It's not bad. Not bad at all. Okay. And let's get the second one. Yeah, it's small wires here, so I gotta do that. Hopefully I'm not gonna be part of the circuit. That'll be just bad news. How much for the second one?
3.7.
3.7. I'm off. Why am I so much off on this one? Let me see if I loaded down the generator. There it is, 3.8. I got 3.8. I was off. 3.8. Whoops. Can you see that?
Yeah, that's good.
Yes, we can.
3.8. So we're close. Not bad at all. Okay. So our values do come very close to our measurements. So there you go. We're doing a virtual lab. How do you like that? What do you think of this lab? Well, it's not a lab, but it's a virtual thing. You'll be doing the same lab in class once we get back, okay? So, but it does work, right?
Yeah.
Yeah. Remember, I didn't check the loading of the function generator. So let me check the loading of the function generator to see how bad that is. I got a funny feeling that's going to be like a little bit off there. Let's see how bad I'm off on that. No, it's close. 5.0. That's pretty good. That's pretty good. I'm surprised. I really am surprised. All right, so that's a serious circuit. Do you want to do parallel real quick, or are you finished up for the day?
I'm down to stay a little bit longer.
Here we got one for staying longer.
I got work to do. They want me to work remotely, so I'm probably going to have to get out of here soon.
Okay.
Yeah, I gotta get going too.
Jeff?
Either way is good for me.
Okay. Let's just do the parallel one real quick. I'm going to set the parallel up, and then I'll put the screen back on, and we could, if you want to do this as when you're finished up, you can share the answers with us. Okay? How's that sound? So parallel is always trickier on this because these inductors are not the best in the world when it comes to trying to fit them in here. I'm going to separate it off a little bit. Let's do the measurements. So if we're doing parallel, what are we expecting to measure? Current or voltage?
Current.
Yeah, it's current. Get up there. There we go. And that's why I want that that meter I have at the college. That way I could get some better measurements on this. So there's that. Actually, I'll keep this one on the bottom. There's that one. There's parallel. So let's put my meter back over. And we can actually figure out the current real quick here, and I'll go switch back to the screen. So I'm going to switch my meter over to current. It doesn't like me. Milliamps AC. Okay, so I'm going to break the circuit, right? You have to break the circuit to measure current. Okay. Might just head back to the campus to get more toys. So we got, write this one down, please. 22.63 milliamps. Okay. You know, I'm breaking it right in the circuit here, so it's might need an extra wire for this guy. Yeah. Polarity doesn't matter. Do I have in the right hole? And I don't. Okay. 6.68 milliamps. 6.63, 6.68. Okay.
For which one? For the
The 100. That's the 100. 6.67, 6.68 for the 100 mils. Good?
yeah.
Okay. Total current. Let's do total current while we have it here, while I still have my circuit set up. Okay. So about 28.34, 35.
For the 51.
That's one. That one's for iTotal. This is iTotal.
Oh, all right.
28.35. Okay. Let me go back and let me shut this guy down. Oops, wrong one. Not what I wanted. Yeah, it was that one. That was the one. Okay. All right. All right. So we're gonna let's do the 33. See what we get for the 33. So this 33 real quick. So this is for, let's call this IL1. That's just V total divided into X of L1. So we already calculated X of L1 because we had the 7 frequencies. So this is just 5 volts. And does anybody have the X of L1 for that one, 33? I got it, 207. I'll write these down. Okay. So if we take, hopefully I'm right. So if I take 5 volts divided into, I get 24. What do we get for L1 for current measured?
Give me a bit.
Jeff, what did we get for current when we measured it?
We got 22.64.
Okay, so we came up with 24.1. Not bad. Okay, not bad at all. All right. There's a lot of things that could be that could change our values. Long wires, that's all going to do it too. So I've been reading on that. Okay, so we come close on that one. How about the 100s?
We measured 6.68 there.
6.68, okay.
Wait, wouldn't it be 5 volts over 33 for L1?
Yeah. No, it's going to be X of L1 because remember L1 is a Henry, so you have to convert from Henrys to inductance.
Oh,
okay.
All right.
Yeah. Okay, I get 7 point. What do we get for the reading from the multimeter on Excel?
6.68.
6.68, and I calculated 7.9, about one milliamp off. Not too bad. Okay, if you add these two together, what do you get on that?
Wait, how did you get 7.9? I got 0.7.
Okay, maybe remember to do mils. Okay, so you're gonna do, so if you take 5 volts, not mils, take 5 volts divided by your resistance, your XBL resistance of L2. So XBL2 should be about 628 ohms. So if we take 5 volts, divide into 628 ohms, you get that guy. So far, so good. So if we take IL1 plus IL2, we get equal to I total. Get about we measured about 28, right? Is that correct? 28.
Yeah, 28.35. But
28.
to go back, Charles, where did you come up with the 207 from the X of L1?
Yeah, I kind
XBL1.
of don't. Yeah, I kind of don't get it. You said
All right, hold on.
2.8.
Maybe I made a mistake with my XBL. 2 times pi times 1,000 times it by 33 e to the minus third. Yeah.
We were working with 5,000.
Oh, that's why. Okay, I didn't switch the frequency over. There's the problem. Sorry, I kept everything at 1K hertz. Sorry, folks.
Oh, so it'd be 1,000.
Yeah,
So-
sorry. Yeah, sorry about that. I should have corrected that one. There you go. So if you
Okay.
did 5,000, you'd be 5 times as high, right? I just kept everything.
Yes. Yeah. Okay, but this is a parallel circuit rather than a series circuit.
That's right. So that's why I had to measure the currents. I can't do the voltages because the voltages across L1 and L2 are 5 volts each, right?
Yeah, in parallel.
Right. So that's why we did X of L1 and IL1 and IL2. That's why I did the measurements on that.
So would IL1 would be 4.8 then? Milliamps?
4.8. Let me 5 divide. I went all the way out, so let me see what you get. 5 divided into 207. I get 2.41. All right. 24.1. I get 24.1 for the current.
Wait, but then you say you had to change the 207 because you did it wrong?
No, I'm keeping it at 1. I kept everything at 1K. I'm keeping everything at 1K.
Did your signal generator was at 1K too?
That's correct. Yes, it was.
Okay, then I got it. All right, it makes sense now.
Wait, so how did you get 207 then? You have
So-
to do 2 pi.
2 pi times the frequency of 1,000. Okay, times it by 33 millihenries.
Got it. Okay. Yeah, I thought we were still working in the 5K, which is
Yeah, I
why my
should've-
numbers didn't agree.
I didn't have
okay.
the screen up. I didn't have the screen up. That's why I didn't see it was 5K. So sorry about that. My apologies on it.
Yeah, I got it now.
Got it now? Okay.
Yeah, we're good.
We're good? Okay. So we just did parallel and series. Pretty cool stuff, right? Wait
Yeah.
till next week. Oh, next week's the good stuff. Next week's the good stuff. Next week we'll get into our RL circuits.
So what do you want us to do for next week in terms of homework and quizzes and stuff like that?
Let's take a look at D2L and let's take a look at all that. So let me just do that. Stop share. I'm going to make sure my thing's up and running. Okay, I could do one of those 2 screens. Okay. I got 15 screens up and running here, so I just want to make sure I got a good screen for you guys. That will work. Share with that one. Okay, chapter 19. Let's look at assignments. Okay, I'm going to move this back over. I need to move this guy over. Okay, so we need to 19. Okay, 19. Looks like 2 people. 19. You at assignment 19. There we go. 19 is right there. So 19. I don't know, it's a space. So under D2L, chapter 19, inductive problems on page 597, I do believe. I lost my book. But yeah, 597. Hopefully it's under 597. Check this for me. But there's all the way up to 24. That's part A.
Like 597 for the problems?
This is
So
inductive problems.
this is your in the assignments. This is what you're calling chapter 19 problems A and problems B.
That's correct. Yes, problems A and B.
These are due when?
We're going to talk about that in a second. And let's get chapter 20 problems out of the way too. Let's do an assignment. I just want to see how many problems I did on 20. 20 is not much. It's like, remember my policy. This policy still holds. If you feel you have the knowledge down, you don't have to do them all, right? So, and some of you may take advantage of that. So chapter 20 is those guys' problems. Okay. So let's go back and let's take care of the due dates for all this stuff. So I'm going to remove the due dates for these guys. Boom, boom, boom. We'll get it. Okay, so the due date is going to be 4/9. Let's go 4/9. And then the last one is not 4/9. This one's going to be 4/16. That way you could get chapter 21 and 20 done at the same time. Does that make sense?
Yes.
Okay. So those are the due dates, and I'm going to make this force. I have to change this to a date out. So this is going to be due on the 19th. Has an end date on the 19th. Okay. Oops, my date range is off. Oh, that's why. 4/9, 4/9, doing. This gives you guys, this is just me. This is my side, cleanup on my side. So, okay. So this is what we have left to do. I'm going to show you what we have left to do. So, so we have 20 and 21. That's next week. And then we have 22, 23. And then we have some filter stuff to do. So I'm looking at being right on target. I'm not going to miss any more days. The advisory meeting has been, right now has been canceled. So you shouldn't miss any days. So, any questions on when homework is due?
No.
No, so from our perspective, we can only see through chapter 20 problems.
Chapter 20, yes. I did not put chapter 21 yet up there. You should not be able to see. See how mine says these has hidden right here? If you want, I can make these visible. I could do that. I could put all the homework up. but I don't want to overwhelm you. That's why I'm not trying to put everything visible up there right now. Right now, I just want everybody just to get, at this point, I would start putting things, all the homework assignments up to May, because a lot of times students are like, hey, I want to just go and, you know, just start getting ahead so I could take my time in other classes. That's fine. But right now, because of this transition, I want to take our time on this. Does that make sense?
Yeah.
Yeah, that's fine.
All right. Quizzes. Last thing is quizzes. You got to know there's going to be a quiz, right? You know there's going to be a quiz. Let's see what we got for quizzes. Inductive, exabel, parallel, transform quiz, inductors. That's 19. So you got these two quizzes. I'll probably put this one as practice, or I'll probably make this active. This one's due